Now we're moving on to the section about Newton's method, and so we have this lesson, Newton's method, and other iterative processes. So Newton's method is a way to find zeros of a function. Like where is it going to cross the x-axis, basically? And so you can restate a function in terms of solving it and trying to set it equal to 0 and developing the iterative process that way, or coming up with what you're trying to get at. So you'll see this in these examples. So an iterative process is one that the next value depends on the previous value, and it goes through a certain calculation and gives you that value, and then to get the third value, for example, you plug in the second value, could be the second and the first. To get the fourth value, plug in the previous, the third value, until you get the value you want. And what we're often after is a certain tolerance, like it's accurate to 10 places. So once you can have the process go twice that has the same 10 places, then you can call that good. And that's basically how, in Newton's method, we're going to come up with show how Newton came up with a process to get this done. Now this will be a general process. It'll be unique to whatever function we're dealing with. So, and it includes derivatives. So we could use all these great skills we've been developing. Okay, so what Newton bases the process off of is down here, this y equals f of x sub 0 plus f prime of x sub 0 times x minus x sub 0, which is what we use for the linear approximation, also the tangent line. Now, in this, we changed some names a little bit. We set it equal to 0, and we changed some names, and we solve for, so this x here would become x sub 1 in this case, or x sub n, where the x sub 0 would be the x sub n minus 1. So solving for that, you end up with this x sub 1 equals x sub 0 minus f of x sub 0 over f prime of x sub 0. So you take the original function, you apply this value put in there, and then you do the derivative with that same value. In a general form, it's this: x sub n equals x sub n minus 1 minus f of x sub n minus 1 over f prime of x sub n minus 1. And I really recommend putting this in a calculator. I use my TI-84 calculator, and I put it in the y equals part, and I use the table to then type in the values to get the next one. Okay, so use Newton's method to approximate the root of f of x equals x cubed minus 3x plus 1 in the interval from 1 to 2, and let x sub 0 equals 2. So that means we're saying, okay, look around 2. So this is kind of like in your calculator, if you're using the TI-80 something calculator and you're looking for zeros, it's like it wants you to say, okay, start here and tell me where to go. That's kind of the idea here. Okay, so let's look at this function. Our f prime of x, it's going to be 3x squared minus 3. So that our formula we're going to come up with, x sub n, would be generated by the previous value, x sub n minus 1, minus the f of x, which was x cubed, minus 3x plus 1 over the f prime of x. I forgot to put the x sub n minus 1. So it's x sub n minus 1 cubed minus 3 times x sub n minus 1 plus 1 over 3 times x sub n minus 1 squared minus 3. So our first term, x sub 1, is going to be, they tell us to start with this 2. So 2 minus 2 cubed minus 3 times 2 plus 1 over 3 times 2 squared minus 3. And from that, I get 5/3. Okay. Now they want us to get x2. So x2 is going to be this 5/3, that previous term, minus 5/3 cubed minus 3 times 5/3 plus 1 over 3 times 5/3 squared minus 3. And from that I get At this point, I started just using decimals because it gets kind of messy. 1.548611. And honestly, I don't do these all by hand. I use my TI calculator, and I put this in the calculator. Put it in a y equals, and then use your table to generate the next set of values. So with that, my x3 came out to be 1.532390161862. When you're in the calculator, go and highlight the actual value because it gives you a rounded off number in the view. x4 equals 1.5320 88989. Now I want to point out here that now we have 1.532 is pretty defined there. It looks like it's settling on this 1.532. So let's try the x5. We get 1.532 88886. So now we're the same all the way down to the first point, the 88. x6 is going to be 1.5320 88886. So you just see these last two were the same amount to 1, 2, 3, 4, 5, 6, 7, 8, 9 places. So if that was your tolerance, you could stop there. And if you're building a computer program to do this, which isn't really too hard to do except taking that derivative, can be hard unless you have another algorithm for that. Anyway, I digress. So that's Newton's process. So what you could do though with this, given your skills, if you're stuck on the island or if you're on Survivor, you can use this to generate your zeros. There you go. Okay, moving on. Here's another one. Let x sub 0 equals 0. Use Newton's method to approximate the root of f of x equals x cubed. So root meaning 0. F of x equals x cubed minus 3x plus 1 over the interval from 0 to 1 now. So it's the same formula. So from 0 to 1. And so we're going to start x equals 0 instead of x equals 2. So as we saw before, our f prime of x was 3x squared minus 3. So x sub n equals x sub n minus 1 minus that x sub n minus 1 cubed minus, I guess I'll slide this over, 3 times x sub n minus 1 plus 1 over 3 times x sub n minus 1 squared minus 3. Seems like it takes longer to write this formula out than to actually do the work. So our x1 is going to be that it starts with 0, so 0 for x sub 0 minus 0 cubed minus 3 times 0 plus 1 over 3 times 0 squared minus 3. So negative 1/3. Oh, double negative, so positive 1/3. And our x sub 2 is going to be that 1/3 minus 1/3 cubed minus 3 times 1/3 plus 1 over 3 times 1/3 squared minus 3. And from that I get 0.3472222. I just want to read it before I start writing it. 0.347222222. And that's it. Okay, let's keep going. Use Newton's method to approximate the square root of 2. So we let f of x equals x squared minus 2. So x squared minus 2 equals 0, x squared equals 2, x equals square root of 2. So that's where they got this, x squared minus 2. And so we're going to start at x equals 2. We're going to calculate x1, x2, x3, x4, x5. Okay, so our f of x is there. Our f prime of x would just be 2x. So our x sub n minus 1, or sorry, x sub n, is going to be x sub n minus 1 minus x sub n minus 1 squared minus 2 over 2 times x sub n minus 1. And we can clean that up a little bit. If we were to divide each term in the numerator, you could say x sub n. You don't need to do this, but this is one way to make it a little easier. X sub n minus 1. And then we'd minus x sub n minus 1 over 2. Then a double negative, so it's plus that 2 over 2 makes it just 1 on top, 1 over x sub n minus 1. Anyway, so you can do that. Let's see a third thing if you want to factor a little bit. So notice you have x sub n minus 1 minus x sub n minus 1 over 2. So that's going to be 1/2 times x sub n minus 1 plus 1 over x sub n minus 1, or 1/2. If you factor out the 1/2, you have x sub n minus 1 plus 2 over x sub n minus 1. I needed that 2 because I factored out a 1/2, so 1/2 and the 2 cancel. Okay, so if we use that formula, our x1 is going to look like 1/2 times 2 plus 2 over 2, which gives us 3/2. Our x2 is going to be 1/2 times that 3/2 plus 2 over the 3/2, which gives us approximately 1.416666, kind of messy, 6666667. So for x3, I'm not going to write it all out. I used the calculator to get this next one. I plugged it in. It's going to be approximately 1.414215686. For x4, we're going to have 1.41. These should start looking familiar to you, like the square root of 2. 1.414213562, and x5 is going to be, I should do approximately again, 1.414213562. So we've repeated the same terms for going out that far, so if that's our tolerance, we'd stop there. Okay, let's do another one. Now we're doing the square root of 3, so that's why they chose x squared minus 3. So our f prime of x would look the same as 2x, but our overall function is going to be pretty much the same. We start at 3 this time, and we're going to just do the first 2 iterations. So x sub n minus 1 is going to, x sub n is equal to x sub n minus 1 minus x sub n minus 1 squared minus 3 over 2 times x sub n minus 1. Okay, so this could be simplified a little bit with the algebra, our friend the algebra. Again, x sub n minus 1 minus x sub n minus 1 over 2, if we divided the top and bottom of the first term. And then we'd have plus 3 over 2 x sub n minus 1. Excuse me, this cleans up just a little bit so that those first 2 terms cancel or subtract. So you'd end up with 1/2 x sub n minus 1 plus 3 over 2x sub n minus 1. So you end up with 1/2 times x sub n minus 1 plus 3 over x sub n minus 1. That's about the cleanest it gets. So our x1 would be, they said start at 3, so 1/2 times 3 plus 3 over 3, and that's going to give us 1/2 of 4, which is 2. Our x sub 2 is going to be 1/2 of 2 plus 3 over 2, which would be 1/2 times 7/2, which is 7/4, which is 1.75. And I think you can see, if you know the square root of 3, it's starting to get closer to it. Okay, that's all they wanted for that. Let's go on. There's another one here. This one didn't print, so let me write it in. It says f of x equals secant x. And so they want us just to write the formula. The iterative formula. So our f prime of x is going to be secant x tangent x. So our x sub n would be x sub n minus 1 minus secant x sub n over secant x sub n tangent x sub n. We could play that a little bit. We could say that that's going to be x sub n equals x sub n minus 1, and the secants cancel, so it becomes 1 over tangent of x sub n minus 1. That should be a minus 1. And I guess you could say, if you really wanted to, x sub n minus 1 minus cotangent of x sub n minus 1. Okay. Got a couple more to look at. So we talk about places that it's not going to work out. So sometimes if you choose your 0 in the wrong place, it can get stuck. So let's try it with this one. F prime of x is going to be 3x squared minus 2. So our x sub n is going to be x sub n minus 1 minus x sub n minus 1 cubed minus 2 times x sub n minus 1 plus 2 over 3 times x sub n minus 1 squared minus 2. So our x1 is going to be 0 minus 0 cubed minus 2 times 0 plus 2 over 3 times 0 squared minus 2. So I get a 1 out of that. My x2 is going to be 1 minus 1 cubed minus 2 times 1 plus 2 over 3 times 1 minus 2. And from that, I get a 0. So what do you think the x3 is going to be? If I plugged in 0 before and I got a 1, then I plugged in that 1 and I got a 0, x3 is going to be giving me, so 0 minus 0 cubed minus 2 times 0 plus 2 over 3 times 0 squared minus 2. It's going to give me a 1 again. And x4 is going to give us, can you predict? It's going to give us a 0. So we're stuck in a loop. Let's go on to the last problem. It says, oops, did not mean for that to happen. Not sure how it did, but I kind of lost it. There it is. For f of x equals x cubed minus 2x plus 2, let x sub 0 equals negative 1.5, find x1 and x2. So my f prime of x is going to be 3x squared minus 2. So my formula is going to be x sub n is equal to x sub n minus 1 minus x sub n minus 1 cubed minus 2 times x sub n minus 1 plus 2 over 3 times x sub n minus 1 squared minus 2. So my x sub 1 is going to be that x sub 0, which is negative 1.5, minus negative 1.5 cubed, minus 2 times negative 1.5, plus 2, I'm going to get out of the screen, sorry about that, over 3 times negative 1.5 squared minus 2. So x sub 1 would end up being negative 1.842105,263. My x sub 2, I'm not going to write that all out because it's just really messy. And that's going to be negative 1.772826,920. This is an 8, not a 4. Okay, I was writing an 8, but it's got small at the bottom. So I'm reading and writing at the same time. So that's it for this section. We have another thing. We're going to talk about some other iterative processes, and then we'll be finished with the part on Newton's method.